Hello, everyone. I'm Majid Nasrollahnejad. I'm PhD student in the University of Padua. I will present our work entitled Peridynamic-based modeling of fatigue damage and remaining life estimation in metallic components. Fatigue is main source of failure in aircraft structures, which 55% of failure in aircraft components attributed to fatigue bonds. There are several distinctly sources of high cycle fatigue damage in aircraft components: aerodynamic excitation, mechanical vibration, airfoil flutter, and acoustic fatigue. So therefore, fatigue analysis is key to aircraft safety and maintenance. Peridynamic is a non-local theory proposed by Sealing to overcome limitation of classical continuum mechanics, especially for discontinuities. This theory is designed to cope with failure analysis since it employs integral equation rather than partial differential equations. With peridynamic, we can simulate crack initiation and propagation. So one of the main advantages of the peridynamics, it enables to simulate crack initiation. The equation of motion in peridynamics takes form where rho is mass density, u is displacement vector, b is body force, f is pairwise force function, hx neighborhood. The interaction between x and x prime is named the bond and identified in the reference configuration. In the displacement configuration, the displacement vector is described by, it's not free. Is described by this equation, and the pairwise force function described with this equation, where C is micromodulus, M is unit vector, S is bond stretch, and mu is history dependent value. A bond breaks when the stretch value exists a critical value denoted by the critical stretch. Now let's look at the remaining life approach, which is used to describe how peridynamics bond degrades over time. Each bond is characterized by the damage variable named remaining life with initial value of bonds. When materials undergo cyclic loading, the bond gradually degrades, and when lambda is equal or less than 0, bond breaks irreversibly. Evolution of this parameter is described in remaining life equation, where A and M is positive constant and epsilon is the cyclic bond strain. Stress ratio in peridynamics defined as the minimum stress divided to maximum bond, and local damage is the ratio of the total number of broken bonds to the initial bond. When this value equal to 0.4, it marks the transition from nucleation to propagation. In this work, we just simulate the crack initiation. In nucleation phase, A and M parameters equals to A1 and M1 and can obtain from the SN data. From slope of logarithmic curve of number of cycles versus to strain, we can calculate M1, and parameter A1 can be obtained from the intercept of this line with strain axis. At first, we validate our model with Sealing results. So for this purpose, we create a model and apply boundary condition as described in the article, fix bottom node in y direction, and apply force for upper nodes. This slide compares our results with Sealing results. As we can see, our model can predict very good and precise. Surface roughness is one of the detrimental factors that impact on the fatigue life. In this paper, they investigate the effect of maximum depths of surface roughness on fatigue behaviors of materials in as-built condition. For this purpose, samples were fabricated using different laser power and laser speed, to achieve various surface roughness. After printing, samples undergo stress relief heat treatment to remove residual stress, ensuring that only the effect of surface roughness would be assessed. For scanning surface, they use computed tomography for each specimen. The full surface of gauge section is scanned and the deepest value of SAV is reported. In fracture mechanics, it is assumed that the largest defect is the site of crack initiation. For simulation, we create the initial value as described in article. Article state that maximum stress is 900 megapascal. Material is Inconel 718. Stress ratio is 0.1. And because of the geometric symmetry, we create half of the specimen to reduce the computational cost. Apply boundary condition, fix bottom nose in y direction, apply symmetric boundary condition, and upper nose is subjected to cyclic loading. This graph illustrates the y displacement across the specimen, giving further insight into deformation behavior. To reduce computational time, we just consider the gauge section here, but however, it is important to verify this simplification effect on the key results like maximum cyclic strain and first bond failure. As we can see, their value are same, so for simulation, we can consider only the half of the gauge section. In addition, the height of the gauge section also reduced to 4 millimeters in order to achieve faster simulation. This figure is the result of for the case with the maximum depth of 85 micrometers. As we can see, crack nucleates from the surface roughness sides, which is in strong agreement with the experimental results. This graph shows compare our results with experimental. Y-axis is the maximum depth of surface roughness, and x-axis for the number of cycles to failure. As you can see, our pre-dynamic results are in good agreement with the experimental ones. Porosity is another common defect in additive manufacturing parts that it has significant impact on the fatigue behavior. Here, we aim to investigate whether in presence of both defects, means surface roughness and porosity, which one of these defects dominate over the others. Experimental results show that maximum diameter of spherical pores is almost 85 micrometers. So we choose the maximum diameter for porosity and the surface roughness, and a distance of 1 millimeter selected between of them to avoid any influence to each other. When pore is located 100 micrometers at a distance of 100 micrometers from free surface, crack nucleate from both of them, but surface roughness dominate to over the porosity. It means that crack here reached the growth stage earlier. Until 20 micrometers, surface roughness dominate to porosity, but in 20 micrometers, porosity dominates to over the surface roughness. Conclusion, experimental results confirm that maximum surface roughness depth in as-built materials plays a dominant role in reducing fatigue life. Pre-dynamic framework successfully validate this finding, capturing defect-sensitive fatigue behavior. When both porosity and surface roughness defects are present in the samples, cracks can nucleate from either of them. However, surface roughness dominates over porosity, particularly when the pore-free surface distance is more than 20 micrometers. And finally, our simulation results confirm the experimental observation that in as-built samples, surface roughness control is more critical than porosity for improving the high cycle fatigue performance of additive manufacturing parts. Thanks for your attention.